So we're going to be talking about EVPN, so Ethernet VPN. A lot of talk about this. I'm seeing more and more customers ask about it. It's funny how quickly conversation will come to the customers, either from manufacturers or from things that they read, and then they start to ask about it. So now it seems to be the answer to all problems every time I'm discussing something with a customer. So really, what is EVPN and why is it important? Well, we've tried to solve this layer 2 stretch for a long time. And what we found out is that Ethernet over the WAN is hard. It's difficult, especially when you start talking about things like multi-homing and the ability to control flooding. So some of the things that happened is with EVPN, we're using BGP as a control plane mechanism to pass routes between PE routers. So what this allows us to do is to control it better as opposed to just flooding it through the data plane. So as anybody who's worked with MPLS will understand that when you're dealing with multi-homing and anything else, it becomes difficult. It adds complexity. And there's been a lot of different ways that they've controlled it over the years, but this is definitely a more elegant way. So with BGP, we're learning MAC routes. We actually see BGP updates now that'll have a MAC route in it. And in fact, later on, we're going to do a demo where we're going to show a vMotion going across, and you're going to see how the MAC addresses are passed across from one PE router to another. So definitely learning from the sins of the past here. So as we're moving forward, we're trying to use a better mechanism. And that's across the WAN itself. So from the PE side to the CE side, we're doing traditional data plane learning. We're learning this by DHCP snooping and also by seeing it from ARP broadcasts. And this allows us to minimize flooding where we can proxy ARP locally. So as we're learning stuff, we're not re-advertising every MAC address locally. And we can support really neat things like active-active multi-homing. So now what we can have is a CE device, and I can have multiple PEs, and both segments can be forwarding at the same time, which helps us, from a redundancy standpoint. And always, whenever you're looking at, 2 links, the question that always comes up with everybody is, I'd like to use both links at the same time. We can also do fast conversions. So if we have a failure on an Ethernet segment, we can quickly fail that over and update next hops without having to learn every MAC address again. So just kind of have to talk about where we're at with the standards. So BGP signaled MPLS-based Ethernet VPN is an RFC now, RFC 7532. And of course, the other part of this that we're going to be talking about is EVPN over an overlay. So in the example we're going to use is going to be VXLAN. But we're still trying to ratify that with ITEF. So as we're going through and we're doing our BGP updates, we're taking MAC and we can do IP routes where we have integrated routing and bridging. And we can advertise them with a new BGP NLRI. So we're using layer 2 VPN AFI of 25 and EVPN SAFI of 70. And BGP allows us to do a lot of really neat things like greater scale. We can use route reflectors, just as we've done with other traditional VPN routes. We support all active multi-homing, and we can do ECMP, so equal cost multipath, load balancing between it. So I knock this over. And one of the things is as we have a segment failure, we can quickly withdraw those routes and update the next hop that are coming. So with EVPN, we're going to talk about some basic terms here. So one of the terms is the Ethernet segment. So as we have multi-homed network, we can identify it as the segments that are attached. We have an Ethernet tag that's a traditional term with, we've done this with VLANs, and it's how we're going to identify this. In some ways, we can bundle this and send this across, or we can do a one-to-one match, and we're going to see that shortly. We have the Ethernet segment identifier, which will represent an entire segment behind the PEs. And one of the other items here is the Ethernet EVPN instance, EVI. That's a routing and forwarding instance, and we're going to represent that so where we collect and store that locally and keep that in a routing table or a bridging table. So here's an example of what it would look like as a general diagram. So we see data plane learning. We're learning, MAC addresses coming from the CE devices. The PEs will then advertise that as a BGP update, and you'll see the MAC address being passed between the PEs, so they're aware of all the segments, all the MAC addresses that are associated with it. And as you'll notice, each of these, it's a simple CE that's multi-home to 2 different PEs. And in this case, we're doing MPLS over the backbone, and we're doing BGP signaling. So with our MAC advertisements, so the original discussion of this, they were calling it MAC VPN at the time. So we take these routes, we're going to advertise this, and it's going to be a type 2 via BGP. And of course, it's great when you try to scale these things. These look great on a small screen, and then when you blow them up, blurry. So when we're using integrated routing and bridging, so traditionally with layer 2, you can have layer 2 and you can extend layer 3 across it. It's really easy, but with EVPN, we integrate it. So we're tying in the routes, and we can have both layer 3 and layer 2 routes being advertised. So we have an extended community for the default gateway that we advertise as well, and the PEs can proxy ARP locally. And this allows us to minimize flooding across the LAN. Anytime you're flooding, it adds to the load on the network, and it also can add, unrequired or undesirable results. As we're going through here, we have a couple different ways we advertise these services. So the first one, you'll see that there's a tie-in between the VLAN ID and the EVPN instance. So it's a 1-to-1 match. On each side, we can do VLAN translation, so we can have different VLAN tags on each side and translate it. And each of these, we're going to have a label that's created per EVI. In the second bundle, we're tying everything together a little bit. We have multiple VLANs being pulled together, and we're mapping it, as I hit this like 10 different times, mapping it per VLAN ID and EVI. And here, the Ethernet tag is the tag value. And we can support multiple bridge domains, and once again, we can do VLAN translation as well. With this last example here, VLAN translation is not allowed. It's a more stringent case. So it's a many-to-one mapping. And of course, the MACs have to be unique across all the VLANs. So now let's talk about some multi-homing here. So there's 3 examples. There is where you're singularly attached, traditional CE attached to a single PE. It's not really multi-homing, but we're going to show you the example. Active standby, where I have 2 PEs. One PE is forwarding, the other PE is in standby. And then all active, where both PEs are forwarding, and we can load balance across them. So on the active standby, one of the P's is going to be elected as a designated forwarder. It's going to act on behalf of that segment and advertise. Couple things to be aware of when this happens is there's a split horizon label that's used as well, or a split horizon tag that's used. So as packets go across the designated forwarder, it's not going to be re-advertised from the non-designated forwarder. And on the bottom here, active, all forwarding, all the way across. Once again, a nice blurry diagram for everyone. So just a single CE attached to a single PE. We don't have to have an Ethernet segment value because there's only one connected. So an active standby, only one's forwarding. An active-active, the CE is attached, and both PEs are forwarding. So in this example, we have an ESI, and it's well known as far as the one vendor is their ESI for that segment. And bump traffic is blocked on the non-designated forwarder PEs. So this allows us to keep from looping. So one of the big issues with this is, okay, I have two connections going out. What happens when a single connection fails? How do I do this? How do I do it quickly? What happens? Well, what happens is when that gets withdrawn, we're going to detect it, and then we're going to go out and update all the next hops. So we're not going out and flooding and relearning everything from a complete standpoint. So we're going to update that for any PE for the MAC IP routes that we're learning from that segment. So unknowns, how do we deal with unknowns? And from this example, this is where we get a little bit of elegance with BGP. So we're going to use proxy ARP locally, and we will respond to ARP requests that we know about. Anything that we don't know about, we're going to drop that traffic. And this limits the flooding. So what's happening is on the data plane, we're learning from the CE. And we're learning all the addresses, any MAC addresses that are behind there. And then we advertise this out as a BGP route to the rest of the PEs. So if we don't know about it and it hasn't been learned, is it really anything on our network? So why flood across the WAN? And at the very end here, each PE will learn the MAC address or ARP entry before we even allow it to pass. So without that information, we're not going to even allow that packet to go past. One of the most important things from this, in just kind of where we see use cases, is we're starting to see this tied into VMware environments and just the ability to do vMotions from one location to another. So as we do this, how does the network know? We're extending Ethernet across the wide area network. How does it know when this host moves from one side to another? It does add complexity there. So there is an extended community with a sequence number, and the higher sequence number wins. So as we vMotion and that MAC address is being learned from another PE, it's going to advertise that route back out. And we see that a higher Ethernet sequence number, the MAC mobility number, is going to win. So each of the PEs will update the next hops. They're going to prune that existing route, add the new route. And then when it finally gets back to the original PE router that was advertising it, it's going to withdraw based on the higher Ethernet segment.
So the other fun thing with EVPN is that we can now start integrating it with VXLAN. VXLAN, if anyone's heard that within the past year or two, it's a nice way to start tunneling layer 2 information across layer 3 as well. What we can do with VXLAN and EVPN together is take some of the strings from one or from both sides, and then make it and get rid of some of the weaknesses between the two separate protocols. So let's first start off with a little quick introduction into VXLAN, some of the building blocks. So we have some basic things going on. We're going to take layer 2 traffic and essentially put on a nice hard candy shell on top of it. And you'll see here, we'll take the VXLAN header, we'll add about 50 bytes onto a single packet, and add it. And with that VXLAN header, we'll start adding things like VNIs or some specific flags. With the VNIs are essentially what you could consider a VLAN on a traditional network. And because of the amount of bytes that we have 24 bits, so about 3 bytes worth of unique VNIs that we can create. That means we get somewhere around 16 million unique VLANs. So that helps with a lot of the service providers out there, allowing them to scale and grow past their original limitations with things like Q and Q. It also means that we have what, about 160 people in here? Was that the rough number? It means everyone in here gets about 100,000 networks that they can create with this today. Point in case. In the wise words of Oprah Winfrey, you get a VNI, you get a VNI, everyone here gets a VNI. So what VXLANs also allow us to do is integrate existing networks. Let's face it, everyone here probably has that massive, ugly AS4000 or some old system that just can't be virtualized. So we use technology called VTEP, or VLAN tunneling endpoint, that allows us to directly connect devices that can't be virtualized into the network, be able to take their layer 2 traffic, things such as trying to communicate to a local firewall, local system. We'll take that information, we'll encapsulate it in VXLAN, and then send it across the network via layer 3. You'll notice here on this diagram, we actually have VTEPs that are both on a ESX host or a virtualized host, and we also have VTEP endpoints on actual switches. So a lot of, as we're starting to see this technology take off, there's going to be a lot more systems that are going to support VTEP. We're already seeing in Juniper and Cisco, and I'm sure that more are coming shortly. So, to bring it all together, why are we doing this? Why are we working with VXLAN? Why are we working with EVPN? So with a lot of common top-of-rack switches, they're often very, very limited on some of the feature sets they have. Yes, they have BGP. Are they going to do full-blown VTEP? Probably not. Are they going to be able to do things like GRE tunnel hashing? Some of the other competing overlay technologies include a lot of GRE tunnels. And unfortunately, in order to do hashing a lot of common switches, you need the 5 tuples. You need source address, destination address, you need a port, you need a protocol. With things like GRE, you don't have that. You only have 3 of those. So unless you're using specific hardware, hashing GRE and trying to get active or trying to load balance between 2 separate links just isn't possible. Just as I mentioned before with IP fabrics, they're becoming more popular. You know, you throw on a basic license on your top-of-rack switch, you can now handle 20, 30,000 routes, which is probably more than most of the CAN tables on those systems anyway. So trying to learn that many layer 2 addresses sometimes just isn't possible. And then finally, with VXLAN, I'm not going to lie. It's actually the service guys trying to interpret how networks should be built. And let's face it, if they can barely understand some of the IP stuff, do you think they're really going to get MPLS? I mean, MPLS is really, really hard, or so they say. Finally, some of the VXLAN deployment options, from a pure VXLAN overlay type solution, what we'll do is it's a data plane protocol. So there's no single brain, there's no central location where we can start sharing routes or information. So with a data plane based type deployment, we're going to have to use things like multicast ping groups to start advertising VNIs. Yeah, that's great and all, but there's some major issues with that when you're starting to do communications from one local data center to another. That's what we call the data trombone. Let's say your default gateway between 2 networks is located in Chicago, and then your actual VMs or your actual devices are located in Boston. For those 2 to communicate, they actually have to go across the MPLS path twice. One to go to the default gateway, one to come back, and vice versa. So that's not very efficient. That's why we want to introduce EVPN, because EVPN will actually be able to use things like proxy ARP to act like the default gateway in the respective data center and keep things local as close as possible. On top of that, when we're trying to flood out new information, let's say we want to learn about a new MAC address or learn some new information that occurs on the network. With a pure VXLAN deployment, we have to use, again, those multicast tunnels. We're going to have to create essentially, everything's peer-to-peer. So again, That's fine and all, that's fine and dandy, but sometimes, especially if we start hitting the upper limits of our switches, like I said, we have 16 million VNIs. No single switch as of right now can support that many VNIs, but as we start to push towards that limit, especially in the service provider networks, just trying to do peer-to-peer communications could potentially flood the network. So with EVPN integrated with this, EVPN maintains a basic list of all the known MAC addresses, all the known VNIs, and then we're going to use the EVPN protocol to actually communicate that out to all of our switches. And then finally, because of that, we're going to have a nice full mesh topology inside of our EVPN with VXLAN network. So today we've got a demonstration, which, did that come back up?
It came back up.
Sweet.
Live demos are always great. It's like,
Yep. So I'm going to switch over the laptops here. It'll take about one or 2 seconds. And we actually have, yeah, go ahead and, if you don't mind, that'd be awesome. Thank you. Just want to show, we're actually going to be working specifically on the VLAN 101, or in this case, VNI 101. We have a couple systems in there that are going to be using the EVPN with MPLS fortifications.
So what we have is we have a couple routers that are set up with connectivity, and we have VM hosts on each side. So from that way we can show a vMotion going across and show the difference of how the routes are being updated, how the MAC addresses are being advertised.
Exactly. All right. So we've got that. Can everyone see the font, or is it too small? Just getting a little bit of yes and no, so I'll try and zoom it in.
It's a Mac. Command plus.
There we go. Okay. So what we're first going to do, I'm going to show you, we've got a lovely little Windows 10 box over here. Yeah, we like living on the edge. And just for convenience sake, we've got the MAC address already pre-recorded, so that way we know we can find this system wherever it is on the network. So I'm going to start a continual ping here, and just let this go in the background. Right now, that location, if I can remember which way my mouse goes. There we go. This is the Windows client right here. That's the Windows 10 client. You'll notice it's in the Boston data center. From here, when we go to VMX Boston here, we're going to do show route EVPN MAC address. And then we're going to put in the magic MAC address. All right, you're going to see a bunch of MPLS stuff. This is, like I said, we're using EVPN over MPLS with this demonstration. But you'll notice at the bottom, there is one MAC address that's learned. This is local to it. You'll see, based on the way that the route is flagged with the indirect, right there at the bottom. Where's that pointer? There it is. There it is. So right down here, we actually have the MAC address that we've learned indirectly. We'll take that MAC address and then re-advertise that back out to our friend in Chicago. So we're going to do show route EVPN MAC address again. You'll see, we actually have we learned two routes. First one's in the specific VNI. So we were talking earlier about the different types of deployments. The one thing that we noticed originally was that when we were trying to deploy this in our lab, it made it easier for us to create a separate EVPN routing instance for each VNI that we created. Now, mind you, that doesn't scale well inside of a service provider network, but we're on budget, we're on time, so this was good enough. Next up, we are going to actually perform a failover of this Windows client. If this actually behaves. And of course, Chrome crashes because that's awesome. So here's what we're going to do instead. I'm going to show you what happens when we do a failover. So give me 1 second here. All right. So like I said, we have that Windows client. It's actually going to be, it's in the Boston data center. We're going to show you, that's the MAC addresses, the stuff that, that I showed you earlier. First, we're going to dump that BGP update not only in the EVPN instance, but then in the per VNI instance. On top of that, we'll do the migration. And you can see here, we're going from Boston to Chicago. Give it about 2.5 minutes, you know. We're also vMotioning storage as well, so it takes a little bit longer. But then, once we see that client has moved over, we now have the MAC address and what's being learned has changed. So the indirect route, meaning the route that we've learned or from just seeing traffic come through on that network, seeing that come in here, we now see that in the Chicago network, and then from there we're re-advertising that back out to Boston through one of the two paths. And that is it for that. Are there any questions?
Yeah, I had a couple of questions. Brand new and data. Number one, you guys talk a lot about the stretch plan. Do you know anyone that's using EVPN BGP today in a single data center to manage all of their MAC running instead of multicast per VXLAN?
We haven't really seen any for just one data center. It's definitely a lot. The customers that we're starting to see it from, they have at least one central data center, and they want to do especially for backups. So they have a high availability or DR center, data center that they want everything to fail over to, and only take a few minutes to actually move all their information over. They don't like using like VMware's VDS for some crazy reason, partially due to all the network topology changes that go into place with VDS, the VMware data site or data center replication, that DRS, excuse me. They don't like all the network changes, the topology changes that go along with that. So that's why we're seeing the EVPN VXLAN stuff. We're using our data center more or less as like a highway, as opposed to being something that needs to be integral with our failover plans. That can become very challenging.
I have one customer that's actually looking at something like that. So we see it where it extends, DCI is usually terminated at the WAN edge. We're starting to see that getting pulled into, we have more capable devices that are closer towards the rack. So we're starting to see that terminate locally, and we have one customer in particular that's looking at that. They're in the beginning stages of looking at it.
What level of hypervisor support is there right now for EVPN and BGP?
None. Maybe I should rephrase that. So NSX is one of the common systems, but we simply just integrate with them via BGP. They do support the VXLAN termination point, but for us and for where this technology lies, the EVPN portion is done at your PE. It's done at your edge route, the CE and the PE. Those guys are the ones negotiating that type of stuff. The way that VMware likes to do it now is they like to advertise specific prefixes. So if one address moves from one data center to the other, they're actually pulling out that 1/32 or that 1/128 and then re-advertising it across the data center. And that way you learn your route for that specific prefix on the other side.
And last question, you mentioned that EVPN drops traffic to unknown destination MAC addresses. Is that a hard and fast rule, or is there anything to deal with quiet hosts that don't send traffic out and time out your MAC entry?
Well, we're going to see ARP entries locally, and we're snooping for that. We're also snooping for DHCP. So from that, we're going to see that information.
So there's no option for that in application?
So if you
If you had to do
It would be platform dependent. Now, the one fun thing about NSX, because we are, we're taking care of networking, we're taking care of the security of those devices, we can actually pull out a lot of that information and integrate it with, I know we're not supposed to name names of vendors, but Juniper is one of the ones I've worked with extensively. You can actually use that information and pre-populate the switching table using something like OVSDB.
And a lot of them are doing that. It's not
So,
just them.
yeah, a lot of vendors are doing that, but that's the one we've gotten to play around with the most. So we're taking information from VMware. Yes, that host is not talking, but we still have every information about that host being recorded. So we'll use inside of our switches or routers or what have you.
Yep.
Question. So if you have your top of rack switch is hardware VTEP,
Yep.
you have your software VTEP living behind that in the exact host, does that cause any issues where you have this chaining VTEPs behind each other?
Not really. Ultimately, wherever we're learning the MAC addresses, whatever's closest to whatever's nearest to closest VTEP, I mean, you're not going to be able to, you can learn MAC addresses technically on your switches, but those are, way that these are deployed, they're essentially using all layer 3 links. There's usually not a lot of layer 2 connectivity on those switches that are being used inside of an EVPN VXLAN topology. So, based on that, we're going to always terminate, if it's from one VM to, if the destination is to a VM guest that's on that host, then the VTEP is going to be terminated on that ESX host. And that's where the traffic will ultimately go. Yes?
Competing technology.
Yep.
It was the question is OTV a companion technology or competing? It's another data center interconnect model.
Yep. Any other questions? Yep.
Yep.
One more.
Yes, but this is the easiest way to handle it going across it, because you either have that or you have to deal with flooding with all the MAC addresses. So it's just representing it locally. Mm-hmm. We're doing so you're doing equal cost multipath across it as well. So in some ways, active-active, it doesn't matter the path. Yep.
For the systems that are implementing proxy, are they also doing the previously heard about V6? Are they doing proxy neighbors or are they just ignoring it?
They support V4 and V6. I haven't tested V6 on it. That's probably one of our next tests. So I will hopefully have an answer for that. We're going to write a blog entry on doing V6 testing with it. In theory, it should be the same. Yeah.
I would comment and say the code quality right now would be something along the lines of when BGP was first implemented in Cisco. Does this kernel actually boot as opposed to does the feature actually work? So, yep, I think that's it. Thank you again for your time today, and
Thank you.
hopefully this was informative and or entertaining.